Так, наш следующий доклад.
Our next report is about interesting cases of JSON using. Actually, we have 2 more minutes before we start, so let's wait, and then I will start my presentation. Can you hear me? Very well. I suggest that people who came here already know these 4 magic letters. And of course, I cannot tell you within 90 minutes about the whole JSON, so this will not be a universal presentation. I will just tell you about the interesting cases which I encountered in my practice, about some of them. People like to code, and they will continue to do so as long as the humanity exists. And there will be more and more interesting cases which will have to be dealt with somehow. Okay. I will begin from a general introduction where the JSON came from. This is truly a legendary story, same as birth of Russian land or birth of Earth. So when we started in 2000, we worked in one Russian company starting with R. And Postgres version was 6.5 at the time. And there are lots of legends that all the projects were developed on one machine, 400 megahertz, and 2 very expensive hard drives of 30 gigabytes each. But this machine was much weaker than any of the mobile phones in this audience. But Postgres already worked at the time. The version was 6.5. And we encountered an interesting task. Join, unfortunately, was working slow. All contents were classified by different types. These were text materials. And between the news and types of texts, there were lots of links which we created with an intermediate table. And we created join, which worked very slow on this machine. Today probably we would not even notice because Postgres changed so much. And we found that there are indexes, experimental indexes. We read about this concept, about the arrays in Postgres, and we changed the table, intermediate table with ints arrays, and created index with arrays. And that's how it started, because it started to work about 30 times faster without join, index search, and we were very inspired, and we decided to expand this model. And in addition to Scholar fields, we started to use arrays, and then we progressed to the next step. The next task has been the necessity to store the polymorphic data. This task started from the first digital economy project in our country, which was called the Unified Educational Environment. And we needed to store in the database the reports. All our schools and higher educational establishments always complain about the number of reports. And of course, all these reports must be stored somewhere. And to store them in a database was impossible because the structure was too complex, and also the number of fields has been also changing. So we created HStore to store the polymorphic data. different parameters for these reports for the Ministry of Education were stored there, and we needed a flexible structure. We coded either in C or Perl. There was no other language, and we created such structure in Postgres in 2003 with the expansion HStore, with certain basic operations to search in index. Currently, I do not recommend anymore to use this function, but at the time we used it, and the graphs, which you can see here, they tell us that when JSON appeared, it became much more popular than HStore. Because HStore is one level structure, and in JSON you have any number of levels. And also it's standard, but it's slightly slower than HStore until now. But it's fast enough. It's useful, it's standard, and it's a good solution, very popular and convenient solution. This is a brief history of JSON. It started less than 10 years ago. In the beginning, people created this expansion to store JSON in Postgres. It was stored there, checked the correctness, but no operations were possible in the database. There were three different types of extensions which realized that in different ways. And later JSON data type was created, and people started to use it. But it was not clear at the time how to use it, because it was just text, and we had to parse it inside the Postgres, which was very difficult. HStore was competing with it at the time, and we thought that maybe it's better to create a multi-level HStore, but JSON won as a more standard solution. And in 2012, JSON-B was created entirely in Russia. It's fast JSON. Some people think that B stands for binary, but actually B doesn't mean binary. It stores the text in the same way, just it has some additional structures which allow to extract the data faster. Using the keys, it's bigger than normal JSON, but faster. And JSON developed so well that in 2016 SQL standards started to implement support of JSON, and all databases support JSON as well. This standard was created mostly by people from Microsoft. They took a lot of ideas from Postgres. Also, they looked at jQuery extension, changed it as usual. But they didn't take a special type for JSON, and that's why in those systems JSON is just a format. There is not so much extension by types. And SQL also doesn't require a special JSON type. Postgres, it so happened that there are two types of JSON. Some things can be done with JSON, some things with JSON-B, and it's not always clear which one to use, and we need to understand very well how they work to choose which one to use, to choose wisely. And recently the support of standard JSON appeared. It was part 1 with JSON pass language. We implemented support of indexes, and the second big part will be released soon, which is JSON table. This is a tool to convert JSON table in normal table. So one way or another, all this functionality has been available for a while, but it was not standard. It was just developed by every developer based on his own needs. So how to choose between JSON and JSON-B? JSON-B is much faster, but not maximum. There are lots of ways to optimize, and soon we will start. But we need to understand that JSON-B is a key of a value, and the sequence of keys cannot be stored. It just keeps the JSTOR as it is, with all the spaces, all the sequences of keys. So JSON-B may be not suitable for you. JSON-B also takes less space, so if you just need to write in a database, just use the normal JSON. For all other cases, if you need to extract fields from the table, you need to use JSON-B, which will be much faster. It supports much more operations. There are different functions for extraction. You can search with indexes, which is written in the documents, and very basic things, so I will not repeat these things. You can easily find them. A big problem in all this is that JSON is a format which came from JavaScript. So this is about hierarchy of data, basically. It was not created even for storage inside the computer, for which there are lots of other types. So when we started to store in JSON and JSON-B, it was actually somewhat a mistake. We needed to store it. We should have stored it in optimized format, and hopefully within a few years we will come to this solution. Currently, the idea is that JSON and JSON-B must become a one type, but it will be a type with parameters which will determine how it is stored, how you can search inside it, what's the additional information is allowed to search faster, etc. Okay, so let's switch to a practical part. Let's move on to practice. Here on the screen you can see the first interesting case. Some people actually code like this. Here you can see a JSON-B field, and people say that, look, this is such a flexible thing. You don't need a rigid structure inside the database. You can store any fields you want. You can store anything you want with different structures. And that's good enough. Why do we need more field, more complications? Let's do it this way. But Postgres is a universal database. This case has certain disadvantages. People start usually from searching data by a certain criteria, and they remember that there can be a certain key or ID, and they realize that one of the fields will be called ID, for example, and it's better to create an index for it. But then they continue thinking, and they compare two types of indexes which are written here. And first of all, they remember that index must be unique if it's a primary key. And how do you think? Is this correct or not? Will this work or not? In fact, this will not work because syntaxis is wrong. We need more characters. And then other people understand that text or digits, by default it thinks that it contains text. And if people want to store index in less space, they create indexes which is better, because if the numbers are big, they take less space as int. And if the numbers are smaller, they take the same amount as text. If you have more than 1 million of IDs, you don't care about speed, about other things. But if you have billions, of course, as digits, they will be stored in a more compact way, and search can be done faster. So second option will be more suitable. You can try yourself and to compare yourself which amount of indexes you will get. And you can even compare the speed of search. And there is one very important thing which I would like to draw your attention. We usually start from 1. But we should not start from 1, but we should start from a big digit, because when we test with small digits, during testing we can miss something. We can observe, for example, that it takes less space. And when the digits are big, you can use it even for IDs. Okay, let's carry on. When we extract the ID, accordingly we will understand, is it good enough or not? So what's next? It will replace the initial key or not? How do you think? No. Okay, now we're reinstalling the Windows. I will just explain that instead of the initial key, only the JSON field was used. Can it replace the initial key? Sometimes, yes. But actually, it doesn't have to be manually, by the way, to generate it. We can use triggers. It's not so easy to write in default. You mean it's impossible to make a return? Yes, this is correct. There are many reasons. 2 or 3 of them are on the slide. First of all, imagine that you want to create a constraint. So some other table would refer to this ID. In syntaxes, you will not be able to write reference what? You need a field. It cannot be a statement. So this is why you will have to use manual trigger for this. And same for auto increment. Insert returning you will be able to do with trigger. This field can be initialized. It's not a problem. You need also null check. And for this you need to create a check constraint that it is not null. Also, there is a situation when the database can understand itself. Where is the initial key? For example, to replicate the updates, the database needs to understand which field is being updated. And in this case, she cannot take the initial key because it's not available. It doesn't exist. And this is why it's better to have the initial key and it's highlighted visibly, because sometimes you might need it even when you do not know about this. So when you extract this ID in a separate field, keep it in JSON. In addition to this, there are also disadvantages for other fields which you need to understand. First of all, we need more space because we store keys. And of course, it takes a lot of space for storage. Also, when we use JSON-B for speed, it also has its overhead. Sometimes JSON-B can take twice more space as JSON, especially if you have short data keys. Also, there is another disadvantage that, let's say, JSON sometimes helps to save space in some cases, but I'll tell you about this later. Actually, in the example which I started, one of the reasons was to store for economy of space. The table was huge with thousands of tables, of thousands of columns, and it was impossible to have so much columns. And some columns were used very rarely for technical universities, one columns, for medical other columns, etc. So it was a polymorphic data. We know that the new column doesn't take much space, but something didn't allow to make them null. So there is overhead for JSON, and there is another important reason why JSON is difficult to use. There is such thing as toast. What is toast? Many of you probably know. This is a way to store big strings. It cuts it in pieces and puts them separately within a certain space. And what doesn't fit, it's cut in different pieces, and the user doesn't see. He doesn't know that in order to extract an ID, it needs to take the whole JSON and then with JSON-B to find this ID faster. This will be easy because ID will be close to the beginning. JSON-B, the fields with short names are closer to the beginning. Index may work, yes, if you just need to find ID. So, toast, actually you do not know where is the field, in the beginning or in the end, but it's not important because in order to extract one field, you need to extract, you need to toast the whole JSON. And of course, for big JSON, it can slow down the system. But in my practice, for example, 1 megabyte JSON can work quite normally and quite comfortable for the users. Just don't put IDs there and don't put other fields in there. Okay, next, if you're looking by index, it's not important if the field is in JSON or not. If you use full scan, then it will be several times slower. Even with small JSONs, the scan will be 20 times slower. If you have JSON, then it will take even longer. Another one, if you're using joins in the fields where JSONs are stored, then the planning software will make mistakes because there is no statistics, and it will give you wrong plans. There is another disadvantage in JSON. As we know, the field can be either int, either text or null. Array, it's part of the structure of JSON. For data, there is no default type of storage, not even talking about other types like geometrical, networks, etc., etc. So keep that in mind because sometimes it can intervene. For example, if you want to validate the data, JSON will not allow you. You need to use some triggers or check constraints which will check. Actually, to have constraints when you work with JSON on certain level, not necessarily on a database level, you need to have something which will control the structure, otherwise you will be lost. Talking about the readability of the code, we're talking about SQL code. In order to operate JSON, you need to write very big SQL structures, and I will show you such structures. So should we JSON the fields or not? Let's talk how we can save space on JSON. As I've said, JSON helps to save space. If we compress several fields into one, and imagine if you archive out of 10 fields, you create one. It will take less space because there is no overhead for the header, and there will be less transaction in the database. And of course, you will have to modify slightly the software to perform search, but you will be able to solve a problem and to save some space. Also, we can combine the fields in one when we archive the time string. And just think about your structure.
So what should we store in JSON? Now, I don't recommend to store everything in JSON, at least not the initial key, but also the fields in which you have any sort of joins, the fields that are uniform amongst all the strings. According to what it's meant to be used for, you need to use the part that is polymorph, the part which is different for each one of the fields. Sometimes you want to have everything in one table, different objects with different structures, but sometimes it's not possible to place them in a single table. And JSON sometimes allows us to very simply conduct searches using JSquare or JSON Path, the new tools which are out. And if you have planned out your structure in a way that you want to use it, great. And in order not to go deeper down into the long-term examples with JSON, I'm going to come a little bit back to the history part. And if you remember, I showed you that everything started with a request for this end partition. And I remember searching for the news here that correlate with certain sections. And now imagine that I needed to find the news that is on the intersection between the two. So I need one that is a part of both, but it is not part of the third. So imagine how quick this SQL will grow. But with the help of the array, we're able to record it all in one short operation. And it is the same thing for JSON. The things that are in SQL very large and cumbersome in JSON and in JSON Square and JSON Path can turn out to be fairly quick. Well, okay, let's get back. Now, I want for everybody to understand that despite the flexibility of JSON, it is well compensated or well supported by some meta description of the structure that will be somewhere inside your database. And it's clear that sometimes you're creating a database where structure changes with time, that is added with certain fields. Some fields are deleted, maybe some more serious things take place, and you're required to save the entire history of changes. And so for the history of changes, JSON is very comfortable. Just throw it all in. JSON doesn't really care what structure you have now. It remembers what structure was, but in order to interpret it, you need it to have saved somewhere. So you need metadata to be collected. And it's going to look something like this. So you have a table which has, apart from the initial ID, you also have the ID of the subclass of the data which stores this data. Then you have the version of the schema, depending if it changes or not. And somewhere you need to store metadata, which is going to describe how your versions changed, and a schema into each of the subcategories that you have in this table. And don't forget to surround this with triggers that are going to validate the data. At least in the test environment. Maybe later you will want to disable these triggers in order to increase the productivity, but just make sure that there is no alterations or no objections anywhere. And the Russian booth can't work if the speaker is not speaking to the mic. Of course, you can use the XML right away. The XML is far more richer, but JSON is simpler. And which is why it gained the popularity that it did. And XML, it's very similar. It has similar functions, but it's less popular because there's less demand for it. Yes, in XML it is all there. before us. But JSON is something that was born down from the roots, what you can say, self-made. Now, for what purposes you may want to use JSON? Now, JSON can have an internal structure, and the field can have an internal structure. Maybe you want to save it as a separate structure, as in the example I've shown. For example, you can have the data for the image, the name of the file path, and maybe you don't want it to be in separate fields, but maybe you want to store it in a single cell, which is an easier way to operate this. And this is a good example in JSON. For example, if you're not only going to store images there, but also files with various formats. For example, you will use for video, you can use things like length of the duration of the video. For the image, you can use the size of the image, and JSON will be very suitable for these needs. Sometimes you're going to have more complex structures. So, for example, the plan of the queries that you get. And you can get this plan through JSON. If you type an explain format JSON, then you'll get a plan in the JSON format. And this plan is a fairly widespread tree that if you will need to archive these plans and then later to analyze for some goals and objectives, then of course other ways are not present. You can only make sure that you keep it in JSON and then use JSON square and then use different aggregators to search for various elements of the plan that you may find interesting. Now I'm going to go side path a bit, how to get a JSON plan together. It turns out that if you explain and you get the explained results, SQL is unable to do anything with it apart from actually obtaining it. Now, if you want to save it, you need to extract it separately into an application and then insert it into the database. Or you need to write down a function. So, for example, you have a function here through which cannot be written in SQL, so you have to use a different procedural language, which is going to extract the plan with the help of using the explain function, and is going to bring it back as text. And as a result of this function, you can either insert it or use it in other ways you may find necessary. And this is approximately how it's written down. Now, please do pay attention. Here you have a number of interesting words that are useful when working with JSON. Now, this function, please pay attention. It is used. It gets the arguments as text, and it brings them back to JSON. And here you have a magical structure, which is called transform for type JSON-B. It is very important. We're going to come back to it a bit later, but do pay attention. We are bringing back the data that here you can see this. This is evidently text because SQL gives this back as text to us, but we want this function to JSON to bring it back in the JSON format, and we connect automatic data conversion from text into JSON, and this is done with the transform command. It so historically happened that, and we're going to talk about this later, that the majority of inbuilt languages are unable to recognize all the possible types, and so we had to introduce the transform command. But we're going to come back to this later. And for now, let's talk about another interesting case. What can you use JSON for? JSON is initially not a format for storage, but for reading. Well, let's just say for data transfer, although that is also technically not exactly correct. But if you read Wikipedia, is going to say that JSON is for data JSON for data transferring is a lie. Although over the past couple of days, I did read a number of articles about Wikipedia, and I figured out that Wikipedia has a lot of things that are not correct there. But I think we need to correct it, and I invite you all to do so because Wikipedia is a collective work, right? Now, let's consider the following subject. We have a library. The library has books have authors, and each book can have many authors. One author can have many books. It's a very typical situation where you have multiples connecting to multiples. And imagine we have 3 tables, classic ways. We have 3 tables. We have book, the person, and authorship. And authorship is also a field which contains the author's identity number, because it's very important. Is it Lifshitz Wandau or Wandau Lifshitz? It's important which one of them is actually writing this. So the connection between them and this separated table is also burdened with a separate field. And now, let's say we need to extract the entire list of all books, and to make sure that the books has its corresponding authors listed to it. So we take this array and we take the surnames of the authors from there. But it's easy and simple when you need to just get the surname. But imagine you also need to take their photos, images. So you need to get many fields. So you need to aggregate not only text lines and strings into your array, but also to get entire masses of data together. And so the question, how can we extract this with one query? And now we can use JSON's aggregate for this. And this is a good application for JSON in life, of course, with all the sidelines and all the exceptions that you have. JSON allows us to gain flexibility in exchange for productiveness. And now this is how the tasks are solved. Now let's have a look at what this consists of. So I'm just going to go across the books, and I'm going to get a sub query where I'm going to try and get all the authors of the books. I'm aggregating the authors in JSON with two functions, JSON AGG, which makes an array from the JSONs, and then row to JSON, which turns the line into JSON, the string into JSON. Now, it's a complete SQL thing, but it's a very specific aggregate here we use. Now, this sort of thing is going to bring us and get us exactly what we need. Meaning is going to get back to us with a list of these JSONs. Now, once again, let's look at a different method. It so often happens that when you're working with, for example, ORM, you need to get out of it not only objects, you need to collect objects from a number of tables, and there are links. Some data is there with the links. You need to get them over. You do some join commands, and you are able to get them all together. And so with the help of the row to JSON, you're able to bring them in all together. And now, without caring for the join tables. And now, for example, let's imagine you take all the books. You get all the information about their serial numbers, about their publishing houses, if they're present. And so the JSON aggregation is a very useful item. Now, why is this bad? Why is it bad to do this? And as I've drawn on the previous slide too, why is this bad? When you're using large data, it's going to be very RAM costly. Yes, you are very correct. When we're using the large data, it's going to take up a lot in general. And the problem is that JSON is very tempting, and we're able to get a lot of data in there, so much data that is later going to be hard to transfer. So we can actually take everything and then sort it out is the approach that, well, we need to understand that the danger is present in such an approach. And sometimes, yes, it is dangerous, sometimes it is not. So when the volume of your information is limited, please do so. When it is not, be careful. And so, for example, we can make the task even more complicated when you need to not only simply extract the information with the books, but you also needed to contain the information about the trees that are inside. And we're going to talk about the branching out trees. So we take a classic table, the sections where you have various nodes of these trees lying down with the parent links embedded. So it's a very classical way of creating this branch out system. And we understand that we can always use out to build this tree fully, or we can make links between the different nodes. But imagine we have an employer coming in, and he said that he tells you that in your query, I want to have extracted the entire path to be extracted, so that I could even get the breadcrumbs on my website, not only the name and the authorship. And now, let's imagine we're trying to do this, and how can we use JSON aggregation to complete this? So we have the test data set. We have a simple tree. We got two branches, classificators, and JSON. We have a Postgres subdivision. We don't need the rest. And of course, we use a Solaris operating system. And let's say the book is called Postgres on Solaris is going to be related to the two terminal, the second and the fourth, and we have to show the breadcrumbs of this book. And we have to do it in a manner that maybe there can be a number of levels. Maybe we can think that there will be more than two. How can we approach this task? From the beginning, we're going to write an SQL in order to build a path from the roots to one of the current points. So here, for example, I took point number 4, Solaris, and I have wrote a recursive CTE that is going to build a path from this particular point all the way up to the top. Now, how are the CTEs set up? The recursive CTE is composed of a union and of two requests, two queries. One is the beginning, and the other one is the iteration, meaning that from the very beginning, you are actually picking this point, the fourth one, with your first select, and then you unite it with the next level. The recursiveness of the CTE is composed of the fact that it automatically unions it until there is something to union, and this thing goes all the way to the roots. This is how the post-recursive CTE is built. And if any of you do not know how this is done, Bruce Momjanov has amazing slides on this on his webpage about the CTEs. They're just great, and he's got a great report of the subject generally. Now, and this thing is able to bring us back with all the points and the ID and the name as we go. The operating system is Solaris, and we have reached Solaris now. Step 2. Now we have to aggregate this. Now, the query that we have sent, we are going to wrap it up in a JSON aggregate in the same way that we've seen before, the road to JSON aggregate. We're going to just call it path. Now, what is interesting here, I'm using the word path in 3 different meanings in this one query. Frequently, we are very hard to find how to change a variable A, B, or X. And because in SQL you also have visibility zones, we can actually call them the same on different levels, and nothing bad is going to come of this. Of course, maybe it's going to be complicated for some people, but some, on the contrary, will find it simpler. And here we use different colors and different instances and different paths. They're all colored differently. And then we bring back the aggregate path, and here is a JSON structure. And now all we have left to do is to unite this. And we have found our way to one section, the 4th one. And we need to wrap it up into something in order to find the array of paths, to find their way to the array of sections. And we'll just take an experimental array here, and we'll just say 2 and 4. Now, the array needs to be unnested, so it turns into a set of lines, strings, so that it can later be used in SQL. And then we do a lateral subquery that contains what has been written on the previous slide. So the 2 previous slides here are outlined in color, and we wrap them into a different query with which they work as a lateral subquery. And at the end, we're going to get these 2 nodes, 2 paths to Solaris and to Postgres. And the last step we have left to do is to unite them with the books and then to wrap it up into a JSON aggregate. And now this is the multi-level construction that we ended up with. It works very comfortably, very quick, unless, of course, you wanted to use it to extract this information for all the books in your library, where you have 10 million books. In the hierarchy, do you have the users? What are you asking me? No, we don't have such a type. No, but there are different ways of getting this done. And now, what is present here? This entire thing here is going to be executed as many times as you are going to be entering this section. As you know, right now, Postgres is not going to understand that you're going to have to cache something or anything of the sort. So if you want to repeat this query massively for every single book like it's written here, then it's going to be very inefficient. But for 1 or 2 books, it's going to be good, and that's how you need to use it. When you have a large amount of queries, you'll need to think about optimization. So for example, you can still carry out this optimization in SQL, but you can lift the CTE above it all. But you can always think about denormalization. A lot of the people who work with branches are actually keeping paths in their initial way, and usually the tree branch data is very rarely modified in order to use complete denormalization. Okay, now let's go on. Now here's our results, but of course we must remember about all of this. Remember about everything that I've spoken about earlier, about the fact that trees here, when we're thinking about trees, we're thinking about them in 2 ways. First of all is a tree that you are extracting from the database, and the second is the tree that dies in a forest. So do not try to get any access information here. Limit your own imagination. Any recursion gives you enormous possibility, especially with JSON. But nevertheless, we already used the recursive CDE, we used the JSON aggregate. Now, what else can we add to this soup? And I would also like to add the window functions. Now, everybody worked with window functions here. Now, if you worked with window functions, please raise your hand. Wow, so many. Okay, we're going to have the simplest of the window functions here. And of course, you're going to see that there are almost no limits to this. Now, before we are going to be talking about the hard, we're going to make a little sidewalk, something to relax. Very frequently, when you're writing down applications for easy clients and you want to get as much as you want to the base to reduce the amount of queries that leave, and sometimes you want to get 2 or 3 or 4 queries into one and get data out straight away. So, for example, you want to get all the various genres and all the various books at the same time, or get all the books and find out how many exactly you got. And with the assistant of JSON, you are able to unite very diverse queries. So, for example, you have 2 options here in a table, and we'll see how well are you able to read it SQL. Are you able to see what is written on the board? Yes, some people can see. Okay, fine, good. So in the first instance, how will the queries be united? How will they join? Especially because in the first query you have JSON AGG written down, so it creates a JSON as an array of objects. So you have 2 arrays of objects, and so these arrays are connected together with these 2 little sticks, the operator or the concatenations. Yes, so of course you're going to have a huge JSON array, which first of all is going to contain the books and then the various genres. And think about it, how you can divide them on the application side. Maybe you can add something into the query so it will be a little more simpler. And in the second case, you need to build up an object from 2 arrays, and there it is difficult to confuse them. Of course, this is also a practical application of JSON. And from the point of view of database, it seems a bit silly, but if you can't apply this logic anywhere else, then you can use them here. Postgres is a universal BDSMR, but it's time to get to the tree. Of course, the trees is a huge topic, and try to imagine that for some reason, for some purpose, you all of a sudden need to collect all of the strings and all the lines that are inside your database in a normal table with parents, and to build a tree, and not any tree, but a JSON tree. Who knows why would you need it? And so you need to get a JSON where you have a tree of points. Now, how would you get this done? And so you need to figure out a way. You want to come up with a way to move around your database with the very same recursive CTE, because what else can you use to actually overcome this? But on the other hand, you have something that stops it, because we know that when we have recursive CTE, every iteration adds more strings into the table, adds more fields into the table. But as a result, we just need one string, or at least 1 per division. We just need 1 tree, or at least a limited amount of subtrees. And how can we do this? Therefore, we need aggregation, because only aggregation is able to reduce the amount of lines used. Now, let us try to approach this task. It is not simple, and in order to solve it, we need some thinking. And I'm going to give you this example, and of course, there's still room for thought there. Now, the plan for the tree is as follows. So from the beginning, we do a simple CTE, which is going to prepare this tree, and then we're going to write an aggregate function that is going to go through the results of the CTE and is going to place each point in the tree into its appropriate place. So really, the aggregate function is a very powerful tool. With its help, going around the database, you can use whatever you want, especially if you have JSON up in your sleeve. And now we're going to have a look at this. Now, there is only a slight technicality. It's always the case in our business. There is nowhere to get here. I'm not only going around the entire tree. Here I am renumbering the entirety of the genres. And so before, if we know the divisions, and so you know that each division had the number of its parent, but did not know its brothers and sisters numbers. But in order to execute the aggregate function, when I'm going to insert every single line into the tree into its place, I require to know, because when they're in the array, they have a certain number. I need to know which one to place in the first position, which one into the fourth one. And so I'm going to calculate these numbers from the very beginning. I'm going to calculate these numbers from the very beginning. And now here, before we are actually going to start to recursively collect this tree together, in the very first object of my recursive CTE, we're going to see a non-recursive query where each section, using the window function, I'm going to, using the window function, give it a number and its position among its brothers and sisters. And so in this case, I'm just sorting them by ID. The order doesn't really matter. All it matters is that it's present. And what did I want to say with this -1 over here? Well, that you need to count from 0. Why? Because you're going to... No, because in JSON, the numbering starts with 0, not with 1, like in Postgres. And so my first element needs to have the number 0. Now, I do this, and then I just add a field with POS over there. And after that, the position sections, I use them using the standard recursive T, which we've all seen a million times. I'm going to turn them into what? Into a set of points, each one of them having a separate path tied to it from the very beginning all the way to it. Okay, good. That's it. And so I have this set of points, and the result looks as following. And so these points, each one of them have their position attached to it. And here I was a little bit sneaky in a way. I was adding some additional words, and now you're going to see why I did this. And so my path looks like this. How path in JSON would look like? Each point is going to be in the key of the key node from the previous point, in bind with the position of the previous number. And here you're going to see that it starts from 0 and goes further. Now we have to use aggregate to go across this, which is going to place it into its appropriate places. And so this aggregate function can be written in the most simplest language, in the SQL language. And as you can see, all we have is one function that is being summoned is JSON bset. JSON bset is a very important function if you're working with JSON, because it allows you to write down in a certain path in JSON a certain value, which is also determined by JSON. Now, what do we do here? We take the current position, and so the aggregate function is a thing that is called for each separate line when you're trying to calculate the aggregate. Now, each aggregate has a beginning state, an initial state, and an aggregate function, which is then modified, which then modifies this state. And then you have the end function, but these are all already little bits and things. We don't really care about that right now. We care about the aggregate function, which we have to write down, that adds to the current state of the aggregate one more line, one more element. And so this is done with this JSON set. So here I add an object which consists of an ID, the parent of this division, and the empty space for its subdivision or subpartition. And now a little technicality in the JSON B set eats up an entire array of text. But in my aggregate, I have a JSON array which I need to turn into a text array now. Yes. Now the symbol of the comment is not needed here. It's there by mistake. Don't look at it. And then I identify the aggregate, I create aggregate. I don't think everybody can see it. If I just lift the screen, will you be able to see it? No? Okay, never mind. Then the create aggregate with such a function in its initial state is just an empty JSON. And we unite it, we type it out beautifully with the help of the function of JSON be pretty, and we get a result. And I didn't even draw it out, to be honest, but if you want, you can try it yourselves. Now, JSet bset function has one flaw which needs to be talked about. So if it has at least one argument that is null, then the result is also going to be null. So if you want to add null inside JSON in any of the keys that you're using, do not think that you are going to be able to place null into this place and it's going to still work fine. With using this, you're going to kill your entire JSON. Now try to look for other ways to do this. And now let's play some histograms. because aggregate is a fairly complicated thing, as a histogram, we're just placing the frequency dictionary just for random values, and we're going to write down an aggregate function for them. How can this be done? Once again, with the use of JSON, the key is going to be the definition the current definition, and its value is going to be the amount of iteration this means. And then we set up a similar aggregate function that is using the same key and the same identifier to use it, and it takes JSON and just adds a 1 to it. Now, pay attention to this entire construct. Now, I need to cast it into int to check if it's not null, to thereby bind it with 0. And then everything is going to work, and we're going to get an aggregate that is going to look approximately like this. And every single time that when you're going to launch this on the random numbers, you're going to see different results. So this aggregate is written on the most simplest language, SQL. You know, you can write a lot in SQL, but sometimes it is not enough, colleagues. Sometimes it's just not enough. And so the fifth interesting case, sometimes we're forced to work with JSON inside other procedural languages, and this is a very deep topic. I'm just going to briefly skim over it right now. As we've seen, the construction for work with JSON based on a B set or on things like this are all there in order to get a ++ throughout the key, and this is fairly cumbersome and fairly inefficient because it takes and recreates this JSON every single time. This is very inefficient, and so there can be cases when you will find it more comfortable to work with other programming language where you can express this easier, more comprehensively, and sometimes even more efficiently. But of course, this is not the case, and okay, wait, we'll see this later. So what languages work well with JSON? Now, there are two, PL Perl and PL Python, that work very well, and PL8, which works very well with now Perl and Python, because of the historical circumstances they're in, receive JSON in text. And if you want to work with it as with a data structure, in order to change it into the internal format of this language, you have to reparse it into disparse it into in an evident way, and in order to disparse it in an evident way, you have to use the transform construct, which I've talked about earlier, and it has not appeared right away. It appeared quite some time ago, but it is universal, and so you are able to use it to write down the function and transformations of all types into the internal understandings of any of the language. And now there is not so many transforms written out for this, but for JSON-B, the transforms are there for both Perl and Python, and PL8 has been done in a different way, but it's not part of Postgres in of itself, but it has a JSON on its internal read, which is much better. And so it seemed that PLV8 is good to use, but you need to understand that for your Postgres version, it may be unavailable. So for example, 12 Postgres does not yet have a released version of PLV8. You have one for Postgres 11, but not for 12. So make sure you choose your language wisely. Now, how can we use PLV8 to write the same aggregate? Wait, no, sorry, this is a different aggregate over here. But what does this do? It sums up the digits and unites the database, so the digits that are there on the entrance, and it starts to accumulate all of this in the array. It looks fairly simple. Here you see a list which it places in, and now for those of you who know JavaScript understands as well. And it lists it and then adds the number to the sum, and this is how it works. And I think that everybody knows that we need to count the money in the script, that we are not allowed to use this method to count money in the script. You know why we cannot use this?
Silence. Who knows why we should not count money like this way? Absolutely correct. The efficiency of the JavaScript is due to the fact that all the digits are float. And this is why, yes, there might be mistakes, but in fact, in JavaScript, we now have digits of any length, but they work slower than float. But anyway, here it's like this. The same can be coded in Perl. In order to work with transform, we need to connect an extension which realizes this transform. I'm sorry, again, I think I coded in JavaScript, my mistake. But in any way, it's similar. Just copy-paste didn't work correctly. So just calculate the speed, how fast these aggregates work, and you will see that SQL aggregate will work 2 or 3 times faster than Perl or V8. And the speed actually will be the same because the task is too simple. In more complex tasks, SQL will run slower. It will delay in the tasks when you need to avoid the tree stored in the memory. For example, SQL will slow you down. I will correct this before I will put the slides on the website. On the SQL, you can code the same aggregate, and I would like to draw your attention to another particularity. For example, if I want to make push in the array element, how can I use JSON bset to add the array? Actually, I can, not using just the specific number, but to put a big digit, which is, we know that it's more than the number of elements. In this case, it will work like push, and it will be written in the last empty field, empty cell. So this SQL aggregate will work 2 or 3 times faster than the same on JS or Perl. Now we're approaching to an end, and let's talk about the bright future which awaits us. So, what do the developers work at currently? If we will not create the unified type for JSON, we'll have to create 2 more: JSON compressed, optimized, and with optimization of storage in Postgres. For this purpose, Toast, it's good, but not for all purposes. For example, JSON data, where we need to take the key from a certain location, or if you have blobs in Toast, and you need a part from the video or something like that. For example, I have a relative who about 8 years ago told me about he stores pictures in Postgres. He stores them in big blobs. These are fingerprints, small pictures. He puts them in blob containers. And he doesn't need to process the whole data, just to use the specific offset and to take exactly what he needs. Another interesting topic is lazy transform. In all languages currently, in B8, in Perl, and Python, we completely transform JSON into internal structure of data. And sometimes it's too much. If it's 1 megabyte, for example, and you just need 1 field, the lazy transform will take it only when you go for a certain field. In Perl and Python, it's comparatively easy to make. The faster search inside means that JSON headlines will contain something like table or tree, which right away will put you in the correct field. But of course, it makes sense only when the Toast optimization is done. Okay, I think that has been enough. There are several links which you can use. These are other presentations with similar information or similar topics. Thank you very much for your attention. Any questions? We're using JSON binary in our structure, and one question from developers. Do you work with IRM developers to implement the structure of JSON binary, maybe control them from the outside? This is a very good question. Actually, no, but we're waiting for them when they will come to us. If you will tell us who we can cooperate with, please give us their contacts and we will tell them how to use JSON. Actually, you can take whatever you need. And actually, I have an experimental project for such RM using JSON. This is a very deep subject. If somebody wants, actually it may help because it's much better than EM. If somebody uses Jira, it has EM. So sometimes it can work very slow. My question is, the JSON index is a standard solution. You said that Microsoft agreed with Oracle about JSON. They agreed on indexes? No, they didn't agree on indexes, and they're not part of standard. In Postgres, we have certain types. The initial key in Postgres goes into index. In fact, for example, when you parse XML, I'm a Microsoft representative engineer. When we parse XML file, it includes initial key in the initial index. Because why do you need to search the whole field if you just need a certain value? You can use indexing differently. This was not part of my presentation, but if you look my previous presentation, the first link on this slide, JSON with examples, there you can find some information about these types of indexes for different types of requests and queries. But there is a lot to develop. For example, we would like to be able to index just some part of JSON, not the whole JSON. In standard, JSON indexes will be included or not, because currently in SQL servers we have to use indexes which are very difficult for JSON. In SQL standard, unfortunately, they're not available and we're not part of committee. So please give an advice to your colleagues. Thank you. Maybe sometime in the future. In the latest versions of Postgres, do you still have joins and GIST indexes and arrays problem? Joins became much faster since then. So in some cases it remains. We need to understand that the more complex is your query, for example, intersection of two tasks, then the probability of join working with the same speed as JSON will be lower. Check-in index is also faster than GIST. They're faster for search. It also depends on the distribution, on the statistics. For example, if you have some part where there is a lot of articles, then the internal statistics is not available in the GIST, and there is no optimization to work with join. And GIST index will not be efficient in this case because its upper nodes will be filled with the same information. So it's actually better, but still these solutions are still applicable and important. Any more questions? If there is no more questions, then I wish you all JSON.